Why is going?
Can I click it?
Behind. Okay. Hello, everyone. Welcome to another session of Seminar in Computer Architecture. For today's session, we have two interesting talks. The first one is about Venice, the work that we published in ISCA 2023. Severin Huber is going to lead the discussion on this paper. Severin is a fifth semester student in computer science. He is quite interested in computer architecture and graphics. And also he enjoyed watching sports, especially football, and listening to music. So yeah, feel free to start your talk, Severin. Thanks a lot.
So welcome everybody to my talk today. I will, as you have already heard, talk about Venice, which is improving solid-state drive parallelism at low cost with conflict-free accesses, which was published in the context of the ISCA 23, which is the International Symposium of Computer Architecture. First, I would like to provide the outline. I will, as expected, start with the summary part. I will head on to the paper analysis, and then at the end, we have a small discussion. So the summary is further subdivided into background. Basically, I will tell you how a normal SSD is built. I will then head on to the path conflict problem, which basically is the motivation of the paper. I will then provide some prior approaches. I will provide the mechanism itself, Venice. I will then head on to the methodology and the results, and at the end, the conclusion. So let's start with the executive summary. So basically, the problem that Venice tries to solve is the path conflict accesses in SST, which limit parallelism. I will talk later what exactly a path conflict is. The goal of the paper is to show the impact of path conflicts and their impact on performance, and then providing a solution that reduces path conflict at a low cost. And the key ideas behind it are basically increasing the number of paths between each flash chips and the flash controllers, and then effectively also utilize those increased path diversity. And in results, it has been shown that it shows a great improvement of performance over prior approaches in performance optimized and cost optimized SSDs configurations. So let's talk about the modern SSD, which is basically built up something like this. It usually has an SSD controller, which has a host interface layer, which basically communicates with the host system and the SSD, which communicates also with the flash translation layer. The flash translation layer has four main responsibilities, basically mapping the logical addresses and the physical ones for every page. It does garbage collection, where leveling, and it caches frequently accessed pages in the DRAM, which is located inside the SSD. There are also the flash controllers, which are inside the SSD controller. They are the main parts which communicate with the flash chips where the actual data resides. Those flash controllers are connected via multi-shared bus channels with the flash chip. And that's why we call this architecture a multi-channel shared bus architecture. Flash chip, just briefly, can be divided into blocks, usually 2 blocks, which can operate independently, which are then further subdivided into dies and pages and cells. And cells is where the actual bits reside, and they kind of determine how much memory an actual flash chip can have. So now let's look at the motivation of the paper, the path conflict problem. So as talked before, multiple flash memory chips are connected to the SSD controller using a shared channel. Usually those numbers are around 4 to up to 32 flash chips that are connected to one channel. When then an IO request attempts to simultaneously access the flash chips using a single path, a path conflict happens. Basically, one IO request already occupies a channel, and another one tries to transfer data, but it can't, and it's blocked. So basically, path conflict then causes the IO request to be transferred serially on a shared channel and not parallel as we would like it to happen. And this limits then the SSD parallelism and reduces performance, of course. Read requests are usually more affected by this because in read requests, the actual data transfer dominates the whole executive the executive service time, which is the one most affected by those path conflicts. Yes. Now let's look at an example. Basically, we have a case where two read requests would like to issue a data transfer or issue a read request over the same channel. This basically cannot happen because one read request already occupies the channel, which causes the path conflict. When you look at it on a timeline scale, the commands issued by the flash controller here on the left side, they usually happen serially because the flash controller only can take one read request at a time. Then the actual read operation happens, which can be served in parallel. And then the data transfer, which is the main performance loss because we have a path conflict, and the data transfer of the second request has to wait. Yeah, basically, first and last one can be served serially, whereas the one, yeah. Now look at the case where you don't, where no path conflict occur, basically where the requests are on different channels. So two read requests over different channels, which can happen simultaneously, which means all those things can be served in parallel, and we can gain a huge performance, and we can save cycles. Therefore, which I've shown you, path conflict increases the average IO latency by 57% in the experiments shown in the paper Venice on a performance optimized SSD, and also the performance overhead of path conflicts basically increase by the factor you see here in the experiments for high IO intensity workloads, which is not good. So now we have seen the motivation of the paper. What has been done so far? There has been some prior approaches to address the problem. So we have the normal setup that I've showed you before, the multi-channel shared bus architecture, where we have shared channels and flash chips, which we call the baseline SSD. Now, one approach would be to increase the channel bandwidth, basically. Such an approach was published and called packetized SSD, which basically makes the shared channels 2 times as wide. Unfortunately, this only decreases the data transfer time, but doesn't really mitigate path conflicts. And therefore, the baseline SSD and the packetized SSD both cannot provide rich path diversity, since the number of channels connected to each flash chip and flash controller are still the same. And also making the channel 2 times as wide has a huge cost overhead. So one approach would be then to increase path diversity. So one approach would be the packetized network SSD. So we have the normal horizontal channels, which you have seen before, and then there is some vertical channels added. So there's basically 2 times the amount of paths between each flash chip to flash controllers. Another one would be the network on SSD, which has basically flash channels between each neighboring flash chips and uses a simple deterministic routing algorithm. But they also have some disadvantages, obviously. Although they have some higher path diversity than the first 2 I showed you, they are not able to utilize the path diversity really effectively, and they also incur a large area and cost overhead, obviously, because modifying the flash chips on network on SD is very costly, or adding double the amount of channels is also not very effective when you have to look at cost. So when looking all at the prior approaches, it's interesting to see how they're done on performance-wise when looking on the speed up or the baseline SSD. Basically, we can see here, we compare it with a path conflict-free SSD, which is basically an SSD which has a separate channel for every flash chip to every flash controller, which basically reduces the path conflicts to 0 since every flash chip has a separate channel. And then we can see here that even though all prior approaches show some improvements on our baseline SSD, path conflict-free SSD has still 4x speed up, which is significantly more than the prior approaches. As a comparison, the best work network on SD has only a 35% improvement over baseline SD, which is still a huge gap. So having said all that, the performance loss compared to the path conflict-free SD is still huge. Now let's look at the solution that is proposed in the paper, which they have named Venice. So to effectively address the problem of high path diversity, they introduce a low-cost interconnection network of flash chips in the SSD. To then being able to identify and reserve those paths, they introduce a conflict-free path reservation for each separate I/O request. And lastly, to being able to fully utilize the path diversity they offer with the low-cost interconnection network, they employ a non-minimal fully adaptive routing algorithm for path identification. So let's look at the first one, the interconnection network. Well, we have basically the same kind of 2D mesh grid of not flash chips, here flash nodes, and bidirectional links. Flash nodes are basically flash chips, and next to it a router chip, and they communicate with an I/O bus. And to each router chip there is or 4 ports connected, which you can route the data. And obviously this provides increased path diversity because there are more ways for a flash chip or for a flash controller to send, or for a flash chip to send data to a flash controller, and there's no modification needed to an existing flash chip, which means there's a low cost, basically. Now, when looking at the conflict-free path reservation, for this approach, Venice uses a small scout packet to reserve the conflict-free path for each I/O request. Basically, we have the same grid as before. Now we would like flash node 8 as our target node. So basically, the scout packet searches the nearest, or basically the I/O request goes to the nearest available flash controller, which issues then a scout packet. The scout packet is sent on its way to the next flash node, and every router in the flash node has a router reservation table, which basically stores 4 main things, which is packet ID, entry port, exit port, and valid bit. And every time a scout packet traverses through a flash node, it leaves its information in here and basically then reserves its path for its purposes. And then it does so until it reaches its destination. And since the links are bidirectional, it then can traverse backwards to the flash controller again, and the actual I/O request can be issued. So when now looking at another target flash node, in a normal SSD, there would now be a path conflict, since all those flash chips in a normal SSD would be on the same channel, which would lead to a path conflict. But since we have an interconnection network, we can simply take another path and reserve another path for its I/O request. So path reservation succeeds in eliminating path conflicts by enabling conflict-free IO transfer. Basically, before every IO request even starts, there's a path reserved which guarantees free conflict access. And the overhead of a path reservation is negligible due to the small size of a scout packet. And when looking at the kind of, for you as a comparison, path reservation takes place in tens of nanoseconds, and whereas the actual transfer of the data takes place in tens of microseconds. So it's really negligible when looking at the bigger picture. So now let's look at the non-minimal fully adaptive routing algorithm. So basically, whenever there is a minimal path, when it tries to use this minimal path, and it only uses its non-minimal fully adaptive routing algorithm when there's no minimal path. Yeah. Now those three requests all have a minimal path, and they have now reserved paths for their purposes. Now we would like to access flash node 2, and we have a request. So basically now the non-minimal fully adaptive routing algorithm routes the package with a non-minimal path to its destination. There are three key problems or challenges that you have to address. First, no deadlocks, which is basically avoided by if a scout packet arrives at a flash node and there's no idle links, it just can backtrack. It changes into cancel mode, cancel its reservation, and backtracks. And if it arrives back at the flash controller, there is just an other scout packet issued. The other thing will be a live lock, and this is avoided by limiting the number of times a scout packet can actually arrive at the same flash node at a time, which is limited by 3. And the other thing is, one might think that it has some overhead since it's a non-minimal path, of course, and the distance is longer. But that is really negligible because in transfer time, the dominant factor is the size of the data and not the path itself. So now, having explained the whole mechanism or the whole idea behind Venice, I would like to go into the evaluation part. Now let's look at the methodology. We're basically using a state-of-the-art SSD simulator, which is called MQSim, and we have 2 SSD configurations, which is basically the performance optimized, which uses fast chips, which has, for example, has a read latency of about 3 microseconds, whereas the cost optimized has a better cost overhead, but has a read latency of 45 microseconds. And we use 19 data-intensive real-world workloads to test those configurations, and then we compare it with the prior presented works, the baseline SSD, the packetized SSD, packetized network SSD, and the network on SSD. And at the end, of course, the path conflict-free SSD, which is the LD SSD, which has separate channels for each flash chip so that no path conflicts occur. So how does it perform? Now, let's look at a speed up over the baseline SSD. Yeah, as you can see here, Venice improves the SSD performance by 1.9 on average over the best performing work, and is able to lie within 45% of the performance of a path conflict-free SSD. On the cost optimized SSD, the results are similar. Basically, we have an proof of performance over the most or the best prior work of 9.5, and it lies within 25% of the performance of path conflict-free SSDs. So we can say overall, in both cost optimized and performance optimized SSDs, we have a significant improvement in performance over all prior approaches. Now, one important thing is how well does it in actually reducing the amount of path conflicts? And I can say it does very well. you can see the rate here. In 99.98% of the times, IO requests do not experience a single path conflict, which is really astonishing. And therefore, it succeeds in mitigating path conflicts by using the prior presented path acceleration and the utilization via the algorithm. There is still some room to grow. The 0.02% can be explained firstly by flash controllers not being available. There are limited amount of flash controller. So if all those are occupied by a prior IO request, the IO request simply has to wait. And secondly, because sometimes there's just a case where there's no path to a destination if all links occupied. Yeah. And lastly, I would like to talk about the SSD energy consumption of the Venice SSD configurations. Venice succeeds in reducing the amount of energy consumed by 46% over all prior works and 61% over the baseline ST. One has to say energy consumption is the product of the actual power consumption and the overall execution time. And since the Venice doesn't have as much path conflicts as all prior works or a baseline ST, this product is obviously lower. And one might also say the power consumption is lower because those interconnection networks don't use as much energy as a shared bus, and there is less power loss due to the simple router design. If you want to look at some other results, you can look at it in paper. So there are power and area overhead analysis. There is a tail latency. There is configuration of different network interconnection networks, and there is sensitivity and the performance on mixed workloads. Yeah. So in conclusion, we can say Venice mitigates path conflicts by effectively utilizing the path diversity it has provided, and with the SSD interconnection network, it improves obviously performance, as stated before, over all prior work, and on a performance based and a cost optimized SSD. And also it reduces its energy consumption by 46% on average over the most prior efficient work, and therefore can reduce path conflict very effectively. And it's also low cost and requires no change to commodity flash chips, which is also a big plus when you're looking at implementing it in the real world. So now, having talked about the summary of the paper, I would like to head on with the paper analysis. So I will start with the strengths of the paper. Path conflicts have been tried to address before with prior approaches. We have seen them before, but no prior approach has really been able to utilize its path diversity, and therefore it's obviously the paper provides a solution that to an existing problem, which is really good in mitigating those path conflicts, and thus so by effectively utilizes path diversity, which hasn't been fully addressed before by prior work. Also, it presents prior approaches. It does some performance analysis on them and talks why they're not working, and then also in the later part connects related work with Venice. And at the end, it does an extensive evaluation on different metrics. Basically, it starts to speed up. It tries to look at the power consumption on the overall area overhead, which is basically really important when you want to deploy a system in the real world. So now look at some limitations or weaknesses. First one, obviously, it has only been simulated so far, so it wasn't actually implemented or deployed in the real world. So certainly it will be interesting to see how well does it when you implement it. And this one limitation I've noted here, and another one will be there are no insights on performance of other topologies with Venice. So Basically, it was stated in the paper that Venice can work on other topologies, so it will be certainly interesting to see how well does it on other topologies, not only the 2D mesh grid, and also maybe some other testing on different metrics with different amount of flash chips or different amount of flash controllers, which will be certainly interesting to see how well it does on performance, although it has a lot of tests already in the paper. So let's look at some personal takeaways. So one, very briefly, I wasn't aware of the significance of the path conflict problem and the overhead it causes for SSD parallelism. Secondly, how to use path diversity effectively, not only providing the mechanisms to have path diversity, and then also using it effectively by using mechanisms from different areas, such as routing and scout packets, which we know all of in networks. And at the end, obviously gain some insight in the components of the SSDs and their bottlenecks, and yeah, very interesting to see. Now, I would like to end the talk with a brief discussion, or where I would like you to participate. Now, having solved the path conflict problem, there is obviously the question, what is the next bottleneck? What has to be solved next to provide further parallelism for SSDs? So has anyone an idea how to increase or further increase SSD parallelism, or where the next bottleneck lies? Yeah.
So I can't really add
Microphone.
I can't really add anything because you described it before, but I would have thought of like different topologies using multiple entry points, multiple flash chips, in a 2D array or in a mesh grid. Yeah, that would be certainly something. I'm not sure if it actually would enhance parallelism. There's certainly different, more research needed. And on different question, I will provide some insight on different topologies, but basically, yeah, it certainly isn't a thing that could be useful in looking at it. But basically, I think what is really a bottleneck is also data transfer time, and data transfer time is not really increased by topology because, or decreased by topology because a smaller path doesn't really affect performance that much, because still the dominant factor is still the data size. Has anyone else an idea on what the next bottleneck might be, or how you could improve?
You said a few times now that the path length doesn't matter, but if we look at the bigger picture, usually you have the CPU quite a few centimeters away from the SSD. Do you think? I think that might be also a bottleneck. It might help if you reduce this thing, because that's on the scale much bigger thing than what you described.
Yeah, on a bigger scale certainly, but I meant more in the SSD itself. Of course, when you look outside the SSDs, there could be some adjustment to do, but inside the SSDs, I think the dominant factor is still the transfer time. Yeah. So one thing that I noted is the limited amount of flash controllers. Does anyone could think of some benefits of or disadvantages of increasing the number of flash controllers? Yeah.
I mean, one obvious benefit of having more flash controllers would be that we can issue more IO requests in parallel and we can get more work done, but that would also incur a higher cost in the architecture itself.
Yeah, just basically what I wrote. Like you said, more flash controllers can issue more IO requests, basically, but there's obviously a cost overhead, more power consumption, and it also increases the overall complexity of the whole SSDs. So certainly an interesting research point, but as still some disadvantages. Another thing would be the limited amount of flash chip and links. Also, maybe another topology could help there to increase the flash chips, but also increasing the links. But increasing links also means more area overhead, which also has to be researched further. One could look at better scale requests to access more things in parallel, or better allocation policies, basically. Another thing I like to discuss is how to improve Venice itself, or the SSD itself, to further use Venice. So usual SSDs are built to host a normal multi-channel shared bus architecture. So is there some things you could think of to change inside the whole architecture of the SSD to make better use of Venice? Yeah.
So you have presented like a 2D array of flash chips, but maybe we could extend that to a 3D array, which would open up even more paths to be used by this pathfinding algorithm, which may even further reduce path conflicts.
Okay, this would also meaning increasing the number of flash chips, basically.
Yes.
Yeah, certainly an interesting point, which I haven't thought of. Increasing the number of chips usually is also very costly, because those flash chips doesn't come very cheap, and you also have a much more power consumption. So I don't know if actually doubling or make it 3D actually provides any benefits, but maybe with the amount of flash chip we have, we could try to stack them on top, which is certainly interesting, but I don't know if it would increase path diversity actually. One thing I might add is, for example, the flash translator optimization. As a brief recap, as said before, it has 4 major responsibilities: mapping the logical to the physical address for every pages, which basically usually it prioritizes pages across different channels. So it likes to use different channels, so it can be accessed in parallel. There's garbage collection, where leveling, which is basically the distribution of write access or write requests over all flash chip. Basically, which an flash block has a limited amount of time which it can be programmed and erased, and by distributing the data uniformly, or the write requests over all flash chips, basically increases the lifespan of an SSD. And the fourth major responsibility is the avoid frequent lookups in the SSDs by caching frequently accessed data in the DRAM inside the SSDs. And obviously this was constructed or designed before Venice was around. So might anyone have some inputs on how you could change some of these things to make better use of Venice?
I have a different question, maybe regarding the thing you said before. Did you describe, maybe I just didn't catch it, how Venice chooses the flash controller which sends out the packages? Because that might also need some different adaptation rather to the normal SSDs, because the paths do change a lot.
So basically, into my knowledge, the IO request that is comes from the host system is tries to use the nearest flash controller in its path, and if it's not available, it just takes another one.
But that's not really always the path that Venice takes, right?
No,
the nearest one is.
It tries to take the minimal at first, but if it is no minimal path available, it tries to use another one with another flash controller.
But does it change the flash controller then regarding to the path?
I think when it is actually arrives at a flash controller, it doesn't switch flash controller, to my knowledge, but I'm not quite sure. But certainly scheduling issues better across flash controller would be one optimization. So basically, where the data resides and where to be accessed as flash controller. Does anyone? Yeah.
Yeah, I think that certainly can affect the performance. Currently, I guess we try to select the flash controller, which is provide a minimal pass. But when it's not available, we try to we actually try the neighboring flash controllers. So we have some heuristic here, but certainly the deciding on which flash controller can affect the performance. So yeah, that's a fair point.
So has anyone else an input on how to change some of these things? There's certainly data allocation. So one could basically make some research on how to adjust the mapping of the addresses. So since we have more freedom now. Since we have more paths, we don't have to look as strictly on where the data actually has to reside, because we have multiple paths which can lead to a path, to a flash node actually. So we can look at maybe some dynamic allocation algorithms, or prioritize blocks over channels which can operate independently, which also could lead to some benefits. Certainly better scheduling, ensure that data access can align with the conflict-free paths, and that actual data sits on different actual data or requests that are cannot be done in can be done in parallel, are issued with each other, and the others are then done after it. Further research can certainly be done in simpler FTL design, and different word leveling approaches. Basically don't distribute statically over all flash chip, but maybe dynamically adjusting on how much they are used or how much they are erased, and increase maybe the lifespan of the SSD by using other approaches of word leveling. There has been done some prior research on how to exploit flash array parallelism by focusing on physical page allocation. Before, obviously not with Venice together, but the result showed that it failed to lay out data actually to so that they do not experience a path conflict, mainly to the reason that the random access patterns of SSTs, inferences of multiple concurrent applications, and dynamic changes in device conditions. Another approach, as you've already mentioned before, change the topology of the whole grid. In my opinion, it is. I think there's more potential in optimizing the FTL, since the overall bottleneck is at least for data request, is the data transfer time, and another topology where you basically have some shorter links or some shorter paths would not greatly affect the performance, in my opinion. There has been some work done on ring topology, where basically which is called the hyperlink NAND, where there's basically they are aligned in a ring, but it actually fails to provide rich path diversity, which is actually the thing when it's built on. So a ring topology is certainly the wrong way to go. And change location of flash controllers. Basically, every time I showed you an illustration, the flash controller was sitting on the left side. So maybe you could think of something with putting in the middle or the top or on all sides. Certainly interesting to see how it affects performance, but as I said, I think FTL optimization has still more potential, in my opinion. And one brief thing, IO scheduling, which was also discussed in the paper. The authors view it orthogonal to the work they have done, and it's basically just an additional layer which tries to scale IO requests, which can be done in parallel, which I don't want to go into deep now. So the last thing I would like to talk about is other use cases for Venice. So basically, Venice was designed to use this as a mechanism in SSTs to reduce path conflicts and enhance performance. So could you think of other ways you can use Venice or in other situations in the computer? Yeah.
I think DRAM would be a good starting point. I mean, it's something similar. We need to access memory, and yeah, I guess we can do the same thing there.
I'm not fully familiar with the architecture of a DRAM, but it's certainly interesting. I'm not sure if there is also like a network topology somehow where you have to access in that way, but it's certainly interesting if you can access the data with Venice that way. But haven't thought of this. Good, so good point. Does anybody else have some other points on how to use it? Like one would be near data processing. We have heard about it in past lecture or prior lectures. Basically, it is the concept of moving the computation nearer to where data actually resides. So basically, don't build computers that are built around processors, but build them around data, make them data-centric. So basically, an example would be that the computations are actually done inside the flash chips, which where then all the operands needed have to be gathered from different flash chips. Does anybody kind of think of any benefits that Venice could provide to NDP? Yeah.
I mean, you can do more computations in parallel if you can move the data with different paths to the flash chips. I mean,
yeah, it's a very obvious kind of advantages. So basically, because you have a more path diversity, you can you have to gather all the operands over one shell. You can gather the operands via this interconnection network, and therefore reducing the time the data has to be gathered and enhancing overall service time. Yeah. Another approach would be, or another situation would be garbage collection, which is critical in introducing fragmentations and maintain free blocks. In RAID operation, the principle or the basic concept is that the SSC controller reads valid pages from victim blocks. It then writes them to new block or new flash chip, sometimes erases the old block and relocates the mappings. And there's certainly data movement can interfere with IO movements. So I've said this before, and I think this obvious, when it's improved path diversity, can efficiently scale both the requests and the garbage collection, since as I already said, we have an interconnection network where we can issue both at the same time, even if in normal STs, they would lie on the same channel. Yeah. So this was my last discussion point. I would like now to thank my mentors for helping me with the presentation and all the details about the paper, Mohammed and Rakesh, and thank you for listening and participating. Yeah.
Hi. Our next presenter is Yannick Montofani. So he's doing his 5th year in bachelor's program at ETH. And the next paper that we'll discuss is it's about SSDs still, but we have an interesting idea which uses machine learning to improve the performance of the SSDs. So Yannick, please go ahead.
Hello, everyone. I'm Yannick Montofani. Today, I'm going to present LeaFTL, a learning-based flash translation layer for SSDs. First of all, I want to credit the authors because many of the schemas that I used on the presentation are taken from the presentation of the authors. So, first of all, what are the problems? First problem is that the address mapping table grows with bigger workload. And also that as the SSD capacity grows, the SSD DRAM is a bottleneck. So what are our goals? Our goals are to introduce a learning-based FTL that can capture more patterns, and also to reduce the memory footprint of the address mapping table. The key ideas are to exploit learning techniques to identify the logic page address to physical page address translation patterns, and to store mappings in learned index segments. And then about the results, I will talk more about them later, but we have results both in simulator and physical SSDs, and a great performance in 1.4 on average. So first, I will start with the paper summary. I will go over some background and motivation, some previous work, then an explanation of what LeaFTL is, a bit about evaluation, and then on conclusions. So this is a schema of an SSD. So over the past years, SSD capacity has increased a lot, as you can see, and also embedded processor capacity and the amount of flash pages and blocks that we have. This is doable, but we have a bottleneck, which is the DRAM controller, which is way less scalable because it has a high cost and limited capacity. And also, since it's a very small environment, it could lead to problem in heat dissipation, energy, and other stuff. So this is a modern SSD address mapping table. Usually, we have a page level mapping, which is a direct LPA PPA mapping. Basically, every mapping needs 8 bytes, and it takes a lot of space because we have a lot of translations. And as we increase the SSD's capacity, also the memory footprint of our table increases, but the DRAM capacity can keep up with it. So what we do, what's done with LeaFTL, it's they try to reduce the memory footprint of the address mapping table, such that we have improvement in SSD's capacity and we have improved performance from larger data cache. We can take a look on other mappings that have been done. So first of all, we have the block level mapping. Basically, instead of having a direct translation, we reduce the mapping by using blocks. This, although it is good, it reduces the memory footprint. We have problem when we have overhead in lookup. Then the second approach is hybrid mapping. Basically, we take apart from page level mapping and apart from block level mapping, and takes advantages of both. But the problem is that we have too much overhead in the garbage collector. So page level mapping is still the most used one currently. There are other optimization done in the past. The first one is DFTL, which is demand-based flash translation layer. It optimizes performance by caching only the most frequently accessed page layer level. So it improves response time and reduces the garbage collector overhead. but it has a problem because in unpredictable workload, it may incur in many cache misses, and it can result in increased latency and wear on flash memory. The second one is SFTL. SFTL exploits spatial locality in access patterns, and it intelligently manages memory by segmenting and caching data. This one also reduces the number of flash memory access, and it improves SSD's response time. The problem is that it only compresses the sequential mapping entries, and as you will see later, we can do even more. So now we'll speak about LeaFTL, which is the new optimization. So first of all, I will go over the learning-based techniques. Then the log structure table, which is basically where we store our data, our new segments. Then the conflict resolution buffer, which is basically a way to address approximate segments. And then handle address misprediction, because having approximate segments, we will have misses. And also a bit about how LeaFTL actually works. So for everyone who isn't familiar with the linear regression, in this slide, we have two kinds of linear regression. First of all, we have the kind with the precise linear approximation that basically is a segment in this case that passes over every point in its bound, we can say. And we can compact the segment. We can compact the segment, and we have inaccurate linear approximation that basically has an error bound. And having a segment, we have a gamma which we can choose that basically allows all the points outside the segment to be implemented into our segment. How we store those segments are stored in 8 bytes. The first point is the starting LPA, which is simply the standard LPA. Then we have L, which is the length of our segment. Then we have K, which is the slope. And then I, which is the intercept, which is basically if we project our segment, where does it intersect with the y-axis. Having those, we can actually then calculate the physical page address using that simple formula. It is also important to state that having a segment, it is easy to infer for the first LPA, for the last one, thanks to the starting of the length. But as you will see in approximate segment, it is hard to infer in the middle one. So having this method, we have a few challenges. First of all, in case we have approximate segments, we need to handle misprediction. Then we have to avoid learning every time the mapping table. So every time the garbage collector comes, or we have a recurring index segment, we need to reduce the overhead by that. And also we need to preserve other core FTL functionalities because it actually needs to work and does the FTL job. This is where we store our segments. Is a log structured table. As you can see, it has many levels. It can have up to 30, I think. And so the topmost level has the most recent segments. And in one level, we can't have overlapping segments. Overlapping, although it's allowed in between different levels. In the schema, we simply have a segment with the LPA start and the LPA end. This is a problem because in the same structure we have both accurate segment and approximate segment. Actually, in our structure we only store the index segment. The other one we don't know. So in case we want to look up on a segment on a LPA, like LPA = 4. we have problems knowing in which segment it is in case it is approximate, because we cannot infer to the middle point of the segments. That leads to problems when we have overlapping approximate segments, because maybe we know the starting point, the ending point, but in case we have two and the LPA lookup is in the middle, we really don't know which one it is. I have an example to explain because it's a bit abstract. Here we have two segments which are overlapping, one from 100 to 106, one from 102 to 108, and we want to look up the LPA equal to 105. To do so, before a conflict resolution buffer, we actually don't know where it is. So we have a new, we could say, storage method in which every time we anchor on an approximate segment, we basically add it to this array, we could say, and it stores every LPA of a segment, and then it addition to each other, and then this one is a nearly sorted list. It means that it's sorted by the first LPA of the segment, and basically when we need to look up in which segment do we have the information to the physical address page, we simply search for our LPA. When we find it, we go to the left till we find a null. When we find a null, then we know which segment we are in by going one to the right. This way, we can address overlapping between approximate segments. Also, it's important to note that based from the structure on the log storage, and also on how it is stored, it's very fast, and it guarantees there are no redundant LPAs, so we always have the right answer. Then we can go a bit in and see what are the operations we can do when in a log structure table. Basically, when we write a new segment, it is appended to the topmost level. It's important to note that if it is an approximate segment, it needs to be stored also in the conflict resolution buffer. Then, in case we do another write and it overlaps with a segment in the level we're currently trying to append it, then the old segment will be pushed to the next level. Also, in this case, if it is approximate, we need to add it to the conflict resolution buffer. Also, when adding, inserting new segments, the LeaFTL will compact a bit, not a lot, but try to reduce the number of segments in our table. When we want to read, simply we start on the level 0. We do binary search because it's sorted. Then if we don't find it, we just go to the next level. If we find it, we check if it is approximate. If it is approximate, then we go to the conflict resolution buffer. And then on the conflict resolution buffer, we get the LPA. If it is accurate, then we just get the LPA, and we go and we can calculate the PPA based on that formula. Also, an important note is the compaction, because after a while of writes, the table will be quite big, and to make sure it is fast and still accurate, we do a bit of a compaction. Is a difficult, I mean, not very difficult, but complex, we could say, function. And basically, it takes a bit of overhead, but it's on only once every 1 million writes. So it's not so often. It doesn't cause too much overhead. Also, we need to talk about misprediction verification, because in case we have approximate segments, we are not actually 100% sure that the PPA we get when translating the LPA is correct. So we use the out-of-band metadata to verify the correctness. Although this is very slow because we actually need to check a lot of flash pages. On average, it's log of gamma flash pages, but we can fix this. We can fix this by storing on the out-of-band metadata 2 times gamma plus 1 neighbor flash pages. That means that thanks to our linear regression, we have an error bound of gamma, and we are sure that the right LPAs is in that out-of-band data. So like that, we can do a verification on our translation, and we are sure that it's not a misprediction. And this method allows a reduction from log of gamma flash pages read to only 1 flash page read every time we look up on an approximate segment. And then we will go over to evaluation. First, I will go over setup information. Then I will go over some memory savings and performance increases. Then I will speak about sensitive analysis, that is basically how it works by changing the gamma factor. Then a bit about experiment on different SSDs, like different DRAM sizes or different page sizes. Then I will show analysis on overhead, and then also impact on SSD's lifetime. So first of all, implementation details. We have two types of, we test on 2 types of SSDs. The first one is a simulator, and the second one is a real 1 terabyte open channel SSD. Then for the workloads, we have block IO8 traces from enterprise server and university server, and also a data intensity application from file bench and bench base. And the comparison is basically done between the DFTL, SFTL, and DFTL, which is the 2 previous work that I've shown, and the LeaFTL. This one, as the y-axis, we can see the memory footprint reduction, and so the lower it is, the better it is. We can see that there is a big reduction on memory footprint. On average, it's 2.9x, but we can see that in some workloads, it's really, really big, like almost 40x. For the second one, I will show performance analysis. On the y-axis, we have normalized performance, which is basically we put DFTL at 1, and then we compare the other to DFTL. We can see a lot of improvement, especially in some workload. We can see a lot of difference between workload because it depends a lot on if we can actually create patterns. So on spatial locality, on segments and stuff. Overall, it's a 1.4 reduced storage access latency. This is analysis on different thresholds. On the y-axis, we have again memory footprint reduction with gamma equals 0 as normalized, and then basically we have gamma equal 4 and gamma equals 16 to compare to. With gamma equals 0, it is important to state that we don't have approximate segments. We have only accurate segments, while on gamma equals 4 and gamma equals 16, we have approximate segments. In this case, we see that we have a 28% reduction average with gamma 16 compared to gamma equals 0. This is basically the same graph, but for normalized performance. And also in this case, the lower the better, and it's 1.3x performance improvement on average. Then there are tests on various DRAM sizes. As we can see on the y-axis, we have a normalized performance again. And although it's better, storage workload is still bottlenecked by available memory space for caching. And we can see that reducing address mapping side improves data caching. And the second one is basically with various flash page sizes. The only problem with this is that, as we can see in the 16 kilobyte page, we have a bit of a slight performance drop. But on average, we have at least 1.1x on improvement on different page sizes and on various DRAM sizes. Then we go over to the lookup overhead, which is one of the two overhead we have. That schema is a bit maybe rough to understand, but on the left, we have the percentage of lookups. Basically, on the first segment, we have from 0 to 90%, so most of it. And then on the other one, we have very few. We can see that in most of it, we actually only stays on the first level to look up on our structure, while when going a bit on the most strange one, we could say, we actually get to a lot of levels, but overall, it only checks 1.4 level on average, so it's kind of good. While the second one on the left, on the y-axis, we have the same parameter, while on the x-axis, we have the percentage of overhead for lookup. And we only have 0.21 extra overhead for each flash read on average. Then, since sometimes you have misprediction, we need to check how many times do we actually have them. So this is a graph divided by the simulator and the real SSD. Basically, the lower the better, because the higher we go, the more misprediction we have. We could see that on the real SSDs, we have some cases in which the misprediction is really high. So maybe in that cases, use a lower gamma or even gamma equal to 0. And overall, most of the workloads achieve less than 10% misprediction when y is equal to, gamma is equal to 16. Important to recall that average misprediction only occurs in only one additional flash read. So the overhead depends on the SSD characteristic, but it's not bad. Then we go over to write amplification factor. Write amplification factor is basically the ratio between the data written to the flash memory and the data written by the host system. It means that basically how much our system amplified this factor, and this is a great indicator to deduce SSD lifespan. So by looking at this graph, we can see that actually our new method, our new optimization doesn't, it's comparable to the DFTL and SFTL for SSD lifespan. Now a bit about, again, for result and conclusion. As we have seen, it is one of the first work, at least in this case, which is done also on a SSD board, and it shows promising results. And improves performance by 1.4 on average. And yeah, and those are great results. Then we can go for the analysis, a bit over strengths and weaknesses. First of all, as a strength, as I already said, it is validated using both a simulator and a real SSD, and it shows the practical validity of the optimization. Then we have a big performance upgrade, 1.4x on average. Is a big improvement, also because it's one of the first introducing machine learning and into SSD's FTL. Then a good strength of this paper, in my opinion, what was the optimization techniques, because yeah, it introduced a great method with machine learning, but it had a lot of challenges to fix. And using out-of-band metadata to verify misprediction or dynamic compaction to reduce the size of the log structured data, I think it's really smart, and it keeps it quite simple so that we don't incur too much overhead. And also, it is, although I have not talked about it a lot, but LeaFTLs integrate really well with the core FTL functions and with garbage collector. And yeah, for the weaknesses, in my opinion, one of the worst, one of the biggest weakness of the paper, it was for privacy, because usually when we speak about machine learning techniques, it is important to have some sort of privacy because we handle data that may be sensible. And although for linear regression, it might be not a problem, it is still important to state that, at least to do some study about it. And yeah, then I'm a bit concerned about the slide performance drop when going to 16 kilobyte page size. That means that maybe when we go, I don't know, with different SSDs characteristics and stuff, we could have some problems. And also on the paper, it's not spoken about storage overhead, that since we changed some SSD structure and we add some structure like, I don't know, the conflict resolution buffer, it may be small, but it was still worth at least evaluating and adding something to the paper. Does anyone want to add something, maybe some strengths and weaknesses? I have a question, I don't know. Okay, then I will go into the discussion. So LeaFTL is one of the first that introduced machine learning into SSD controllers, and we move away from heuristic-based FTLs. And I want to ask you, do you think it could be useful to use in any other system? I don't know, in storage, in other controllers?
In one of the papers that was assigned as a homework last week, the self-optimizing memory controllers, a similar idea was implemented there where basically the memory controller had a reinforcement learning approach, which is a pretty big part of machine learning. And it seemed to work out quite effectively, just like it does here. So I think it would be, I mean, it is very useful in basically any kind of environment that needs to dynamically adapt to whatever is being fed to it, such as a memory controller or an SSD controller.
Yeah, exactly. I agree. And I think in this case, we use linear regression, which is quite a simple one because we have a small system to work with. But do you think, as is stated, there is also other part, but do you think we could use like more complex method, like, I don't know, neural networks and stuff?
I think that depends on where you use it in the system, because obviously computation becomes more expensive and storage is also a problem. But I think in SSDs, neural networks might also be something that could be used. I know of one paper that uses neural networks in SSDs, and I think that current SSDs also have quite sophisticated memory controllers or a computing unit on the SSD itself, so that might also make it easier. So I think in SSDs, neural networks might be a case, but otherwise it might be difficult.
Actually, I thought the other way around, because SSDs is quite small, and yeah, it could be useful, but we might incur in too much complexity, too much overhead. So maybe in some bigger structure, we could use actually neural network. These are a bit of the works that actually used maybe some different models or different on different system, mainly using reinforcement learning and also online reinforcement learning, which is basically adapting to the data as it comes. And yeah, for the second and last discussion point, I wanted to talk about privacy. Because nowadays privacy machine learning is a big concern because there are a lot of models that needs a lot of data, and it is sometimes difficult to gain that data and it being secure and without problems regarding privacy. So I wanted to ask you if it is actually possible to preserve privacy, and if yes, how can we do it?
I mean, a very good way to ensure privacy is maybe we could encrypt the data, and then when it's being processed, or we can encrypt the data, and then when we need to process it, decrypt it again, and then process it in our model.
The problem is that there is actually problems with the learning and I don't know, the not safe environment is the one of the machine learning model. So if we decrypt the data before going to the machine model, that's a point of attack for. So yeah, encryption might be a way, but it might be a problem to make it happen. Does anyone have any other idea? Okay, so encryption is a great idea, but not normal encryption. We use homomorphic encryption, usually fully, because in that way we can encrypt more times. And basically, our new model learns the data encrypted. It doesn't decrypt before learning, and it's encrypted in a way that it still keeps its characteristic to learn from it. So it is a good choice, but it has a bit of downsides. The first one, we have a slight increase in training time and a slight drop in accuracy. Slight drop, I mean like 5%, it's not a lot, but still a bit. And also a bit of overhead when decrypting and encrypting data. There are also other methods which I think are not so worth it in our cases like in SSDs, but there is differential, I don't remember the second word, it's differential basically when we have a large group of data, which is usually to deep learn on it or something like that. There is a text, it is shown that you can actually see if when you put, if you have a data, you can check if the data is inside that group of data that it's centralized. And a way to fix this is to put noise on data that we have. This is a way, but not in this case. Also, there is federated encryption. I don't know. I don't actually remember the word. Sorry about it. But what? This one was the first. The second was federated learning. So basically, how does it work? It basically decentralizes the data. Simply, when we want to deep learn on a new model, we give the model to someone. They use their own data, so they can keep the privacy and stuff to train the model, and then they give you back the model trained with your data. So they make sure that your data doesn't ever leave the trusted environments. Someone anything to add? Maybe some questions about it? Okay, then I think I'm finished.